As Kermit and Friends might say, it's time to play the music, it's time to light the lights, it's time to talk some AppSec on the AppSec show tonight, or today on Monday. Because this means this week we talk with Andrei Serban from FuzzBuzz about strategies for building tools for devs to use, targets for devs to fuzz, and fuzzing results that drive higher quality software. In the news segment, attackers siphon source from misconfigured SaaS. Surprise. Attack on Titan scours keys for secrets. Low-quality software saps security budgets. 7 DevOps domains for adoption, and more. Why don't we get things started and stay tuned for Application Security Weekly.
This is a Security Weekly production. It's the show to learn the latest tools, techniques, and processes necessary to understand DevOps, application security, and cloud security. Your trusted source for the latest application security news. It's time for Application Security Weekly. Security teams need visibility into Linux systems to detect and investigate incidents and protect against unwanted activity. Operations teams are not down with downtime, and with revenue tied to uptime, ops priorities are enterprise priorities. Which is a higher priority? Why not both? Capsulate provides flexible, production-ready infrastructure protection for Linux systems, all without a kernel module. With ops-friendly production security, Capsulate delivers monitoring, detection, and response without adding operational risk or cost. Visit securityweekly.com/capsulate today to request a demo. In a fast-paced tech environment, the potential attack surface increases with each release and new app created. Detectify automates cutting-edge knowledge from trusted ethical hackers into the development pipeline for reliable application security. Go beyond the OWASP Top 10. Check your web apps for over 2,000 known vulnerabilities actively exploited in the wild, monitor subdomains for potential takeovers, and remediate security issues in staging and production. Learn more with a free trial at securityweekly.com/detectify. Go hack yourself.
This is episode 136, recorded January 11th, 2021. I'm your host, Mike Shima. I'm here with Matt Alderman. Hello, Matt, and Happy New Year.
Happy New Year. Go Bucks. Do you know the response to OH? Sorry, it's the championship game tonight.
Sorry, what were you saying about how cool Penn State is? I missed that part. We also have with us John Kinsella. Hello, John.
I've got no horse in this football thing at all.
Well, we've exhausted my football knowledge at the moment anyway, so it might as well be a good time to read some announcements. Do you all want to stay in the loop on all things Security Weekly and college football? Visit securityweekly.com/subscribe to subscribe on your favorite podcast catcher or our YouTube channel. Sign up for our mailing list and join our Discord server. You could be talking with us live right now. We have officially wrapped up all of the recordings for our 2020 webcasts and technical trainings. Stay tuned as we build out our schedule for this new year. Visit securityweekly.com/on-demand to view all of our 2020 recordings. Andrei Serban is the CEO and co-founder of FuzzBuzz, a security startup based in San Francisco that builds fuzz testing tools and infrastructure to help developers find severe vulnerabilities and bugs in their code with minimal effort. Today, FuzzBuzz works with some of the largest tech companies to reduce the number of vulnerabilities that make it into production by enabling teams to fuzz test as part of their DevSecOps pipeline, finding bugs as soon as they get introduced. Andrei studied computer science at University of Waterloo before dropping out to start FuzzBuzz and accept the Thiel Fellowship. Hello, Andrei. Thank you for joining us.
Hey, happy to be here.
We're happy to have you. And as I introduce you, there's some neat things about fuzzing, and we've talked about fuzzing quite a bit over the past year or two here. But one of them is that we can use fuzzing to find severe vulnerabilities and bugs, and you do so potentially with minimal effort. But that minimal effort maybe not always be true. So why don't we start there, maybe with a little bit of just what is fuzzing and how can we make fuzzing easier to adopt? Because I also want to say not everybody's doing it right now.
Yep, totally kind of right on the ball there. Not a lot of people are fuzzing, and I think the largest hurdle to mainstream adoption for fuzzing comes from just the ability to actually start and kind of write some fuzz harnesses, some fuzz tests. I think that process is kind of the last thing that needs to be worked on. I think there's been a lot of fuzzing research that's proven that fuzzing is a very effective technique. We just haven't gotten it to the point where it's something that every developer can do. And so backing up a bit, what fuzzing actually is and the way it works, which I think a lot of the viewers are familiar, so I'll kind of just quickly go over it. At least the way we do it, we call it coverage guided fuzzing. And so the idea there is you have your application and you have your fuzzer, and your application gets instrumented at runtime, or sorry, at compile time with some flags to be able to give some coverage data back to the fuzzer. We kind of expand on this idea and send other types of data back to the fuzzer, but we instrument this application and then we run it. And then the fuzzer will send random data, random inputs into your application. Your application will then process those inputs and send back to the fuzzer kind of what happened when that input was being sent in. The fuzzer will then take that input and kind of that data and then kind of generate a new input based on that. And so the way that I like to think about it is like playing a video game. If you play a video game and you have to restart to the beginning every time you die, it's going to take you a really long time to get to the end of the game. But if you're saving along the way and you're kind of just incrementally getting a little bit closer, then you're going to finish the game in a normal amount of time. And so coverage guided fuzzing is kind of similar in that sense. It's incrementally getting deeper and deeper into your code by just trying random stuff, but saving the interesting ones and building further off of those.
Yeah, no, that's a great overview, and it's helpful to also think. The video game's a good analogy. So you finally get to the end to find out only that the princess is in another castle. But in this case, it's not completely random. All of the way it's building these intermediate save states, so to speak. There's relationship here to perhaps unit tests, or the way that you mentioned too. I think a little bit guided coverage. So there's a little bit of focus here about how a fuzzer can get to a point that causes a crash. And I think part of that perhaps ties into, how efficient is it to run a fuzzer to find these types of vulnerabilities, or what types of vulnerabilities is it going to be able to find?
Yeah, so the way we think about fuzzing is kind of, if you're familiar with like kind of the known, known, unknown kind of framework, right? Known knowns are the things that, your developers know. They expect to break, they expect things to happen. Known unknowns are things that, they expect might happen, but they're not quite sure how or where they manifest. And so known knowns are things you're testing, things like unit tests, any kind of like developer written test. Known unknowns, you probably want to employ something like a static analysis tool or something like that, where the static analysis tools are just looking for existing bugs or things that have happened in the past and just kind of pattern matching your source code to any patterns that have been vulnerable in the past. Where fuzzing really shines is in the unknown unknowns, right? It's the things that no one knows can happen, right? And the reason it's really effective in that situation is because it is random, right? It's coverage guided, but what I mean by that is that it will just randomly flip bits. It'll just randomly insert characters and append things, slice things, just do whatever it can with those inputs. But the thing is, it saves the interesting ones. The interesting ones are the ones that cover new code paths. They get incrementally closer to finding, kind of getting to 100% code coverage. And that's kind of the goal there with the fuzzers is they're guided by coverage. They're trying to just get as much kind of coverage as they can inside of your application. And so because of that, it really shines at finding these kind of edge cases that developers tend to miss. And so fuzzing has traditionally been very effective at finding memory leaks, crashes, hangs, any kind of undefined behavior or assertion failures, which make up a large part of kind of like the typical CVEs that you get. We're trying to expand the class of bugs that fuzzing finds. And so we do that through a variety of ways, but largely just kind of employing, some of that static analysis kind of pattern matching tooling, detecting areas of your code base that could be interesting to fuzz, and then fuzzing against those areas specifically. Again, the thing to remember with fuzzing is the fuzz engine is only going to be as effective as you make it. It's by default going to look for anything that looks like a bug, right? And a bug is a crash in every case. But if you take a more complicated kind of business use case, right, where you have a bank and you're transferring $10 between two accounts, the fuzzer will send that $10 over. But if actually, $1,000 got sent over, the fuzzer has no idea that's wrong, right? And so you need to tell the fuzzer what a bug is. And so that's kind of the process that we think will unlock kind of more larger adoption of fuzzing is what kind of class of bugs can the fuzzer find? And the way to do that is to tell the fuzzer, these are these are bugs and these are not. And kind of like invariants, right? If you've ever done like property-based testing or something like that.
Andrei,
Go ahead.
Yeah, I was going to say, one of the challenges with application testing in general is kind of the business logic piece, right? Interactive testing has tried to address aspects of the business logic and inserting that into the test case. What you just described sounds like you're also trying to do some of that business logic at the fuzzer as well. So if you potentially can find some of these like logic bugs earlier in the process.
Exactly. Yeah. So the idea is that a lot of the time fuzzing is kind of done at the audit stage, like security audit stage, which happens, once a quarter, once a year, whatever. We think fuzzing should be done continuously. It should be in your DevOps pipeline. It should be run all the time. Anytime you make a PR, anytime you make a new push to main or master branch, right? Like these things should be kind of actively being fuzzed, and because they're changing, right? Like when your code base changes and you're you're releasing multiple times a day, these are all kind of potential introduction of new bugs. And so the kind of core thing that we do is put this into the DevSecOps pipeline, and then you're checking for these logic bugs. And so as long as you can tell the fuzzer, like, this property always needs to be true, then the fuzzer will detect if that property isn't true, right? And so that, a really good example, kind of like I said, is crashing, right? The property needs to be that the application is running. If the application crashes with kind of like a bad exit code, then that's clearly a bug, regardless of the software that you're writing.
Yeah, I think that to help expand on that idea too, that we're talking about business logic, those types of vulns, and it's not just to say fuzzing. If you have a memory unsafe language, just use fuzzing. It's more, I think, if you want to go track down some of those complicated business logic, or even also concretely, what are you parsing? We've seen fuzzing being used quite successfully against parsing of images or PDFs or that type of user-generated content, as well as even protocols. Protocols are great for fuzzing because they have ostensibly a state machine that you're supposed to go from this state to this other state. Here's some well-defined transitions, but maybe the RFC is underdefined, or the RFC is misinterpreted or misunderstood, or just implemented off. So all of these things, I think that business logic, parsers, protocols, these sound to me like great things to go and start fuzzing. I'm curious, looking either at this group that I've just kind of enumerated or some other types of code, have you found some particularly interesting vulns that pop up that could just kind of highlight what it means to benefit from running fuzzers against various types of code?
Sure. So I got to be careful with, I guess, how much I say, but so these are kind of real bugs that we're finding on some of our customers, the ones that are running on our hosted version, at least. Typically, so I think kind of the more interesting ones that we found, we did find a kind of vulnerability in kind of like a medical device protocol. So medical devices don't communicate over HTTP or they have Bluetooth and stuff, but they use random protocols, kind of grammars, kind of like JSON, but like specific to the medical industry. And so like HL7, DICOM, and then there's very specific ones that large medical kind of companies will kind of have just defined internally, so that their devices communicate over this weird protocol as well. So these things are typically so obscure that there isn't like a common framework that you can just pull into your language. Like an every language has an HTTP framework that's kind of more or less standard, and it's really well tested. And the HTTP kind of RFC is really well understood as well, and people know how to test that and make sure things are working. With some of these more obscure protocols, it gets a lot trickier. And so you have these really kind of long, crazy specs that are getting implemented kind of custom by each company on their own, by their own developers. And they will often have mismatches between versions and stuff like that. So that's a really good use case for something that should be fuzzed. And we found some pretty interesting vulnerabilities there that kind of, just in the parsing logic code and the way the inputs get processed by the application. Again, they're parsing them incorrectly and then passing them along to the logic part of their applications. And we found some bugs that lead to RCEs, that lead to kind of memory leaks that you can then kind of read data from from the buffer and stuff. So there are some pretty severe vulnerabilities there. In the more kind of non-traditional case, right? So fuzzing is very traditionally really good at crashes, memory leaks, and so on. We have found some interesting bugs where if you're fuzzing two applications at the same time that should be implementing the same spec, but they kind of differ in their implementations, right? So this is really, really a common thing to fuzz in crypto, either cryptocurrency or cryptography kind of industries, where you have a kind of implementation that you want to build a separate implementation of, and you want to make sure that the inputs are kind of processed the same way. So we found a lot of vulnerabilities there as well, where if you can find that an input is processed differently in by a crypto library, that can lead to a lot of serious vulnerabilities as well. And then lastly, we have found a lot of vulnerabilities in like databases. Databases get really complex, right? They're distributed, they're processing a lot of kind of code, they're high frequency, like they're going really fast and stuff. So you get a lot of interesting vulnerabilities there. Again, more on the side of like crashes, timeouts, and incorrect parsing of like SQL, especially when you get to the really, really crazy SQL statements. You get some really interesting use cases there.
So that's neat. And what you're saying is that you rattled off a couple instances where you're talking about some RCEs, some nasty vulnerabilities. But I think the end too, you're saying, a crash is a crash. And I'm going to foreshadow a little bit. We're going to be talking about software quality in the upcoming news segment. But I think what I'm getting at here is that if you're running a fuzzer and the target crashes, that's actually something to fix. So it's very rarely the case that you're going to get false positives, so to speak, out of fuzzing, right?
Right. So that's kind of I think the most interesting part with fuzzing compared to some static analysis tools or CV scanners is the application that you're testing is actually running instead of just scanning the code. And so that leads to results that are much more actionable. When we report a bug to a user, we tell them, look, this input triggered this stack trace. Here you can go and download it. You can go and look at the state of the application when that happened. We'll actually also try and reproduce that bug ourselves about 5 times, and then let you know how many times you're able to reproduce it. 95% of the time, we're able to reproduce it, 5 out of 5 times. Sometimes you get into state kind of situations where it wasn't the last input that triggered the bug, but it was like the previous 2 or 3. And then in that case, that's where you want to start employing some snapshotting. You want to run the application with debug symbols, so you can give the user an exact kind of debug state snapshot, and then they can go in and look at the exact state that triggered the bug. But for the most part, they're very reproducible. Again, if your application crashes, it's here's the input that caused that crash. So it's very straightforward in that sense, compared to some static analysis tools where it gets a little trickier to detect, like, is this code actually being run this way? It's because it's just scanning your code. So because of that, we think it's really powerful. We're constantly looking at ways to improve the types of bugs that you're finding, because again, they're more actionable. They're more they're less likely to be false positives. So it's really interesting to see what other kind of classes of bugs can we find on a real live kind of running application.
Andrei, the scanners will say, well, I don't need any instrumentation to do what I do, which is scan, statically or dynamically. How difficult is it to instrument one of these applications to get the benefit out of fuzzing? Is it a big lift, or is it pretty straightforward when it comes to the implementation side? Because I think to get to that coverage, you need a little bit of that insight, right? And so if there's too much friction, then maybe the developers don't put that instrumentation in place. What's that like?
Yeah, so that's definitely, I think, it's definitely the largest problem in the fuzzing community so far. We've got some solutions that we will be launching this year, where basically we help developers, familiarize themselves with the tooling and have a better understanding of how it works, and then give them the tools as well to just instrument much easier. So typically, if you want to instrument your application, you need to change your build steps quite significantly in order to account for that. So what we can do is, with most languages, I'm going to put an asterisk there for C and C++, where I think, unfortunately, that's something that might take us a while to tackle. I think, we typically, with C and C++, it's harder to infer things. But when you're looking at languages like Go, Rust, Python, C#, Java, these are really easy to infer. And so what we do is we basically just take your standard build steps that you use to build your application as you launch it to production, and we try to instrument just based off of that. So we're actually not, for certain languages, we're not requiring the user to really modify their build steps at all. And I think that's a pretty big breakthrough, because typically, there was a heavier lift involved. And so we've seen some of our customers take, so it depends on the scale of the company and depends how kind of the large the code base is. We've had some really large databases that kind of onboarded within 2 days. And really that was mostly actually bugs on our side, just being able to handle their scale. Actually instrumenting the code was not the difficult part. And so we've seen kind of on the medical device side, right, those get a little bit more complex. There's multiple pieces, moving pieces and stuff. Those will take about a week to integrate. But once they're integrated, right, there's no more work that the developer has to do on the instrumentation side. Then the developer just has to write a fuzz test, which we make it as easy as writing a unit test. So we provide a lot of tooling to allow the developer to think the same way they think about like standard testing, like unit testing, when they write these fuzz tests, which is, I think, been a large problem that we found is fuzzers work on bytes. And that's really annoying for developers to think about. How do I convert these bytes into the types and structure that I need? If you're writing some JSON, it's really unlikely that the bytes you got from the fuzzer are going to convert directly into some proper JSON. So we provide a lot of interesting tooling that developers can use to just say, I just want some JSON, and just fuzz the data within that. And then, they write this simple fuzz test that they can run locally, but they really don't have to, because they just push it up to, GitHub, GitLab, whatever, and we'll pull it from there and basically just start fuzzing it on our server. So the developer is actually pretty far kind of removed from the underlying infrastructure that's required to actually run these tests. They can just have, they just have to say, like, these properties need to be fulfilled. This is the application, this is the function I want to test, in this structured, protocol or whatever grammar. And then that's it. And then we take care of everything else.
Yeah, that answer. Oh, Matt, did you have a follow-up?
Sorry. Two questions. You're touching right on something that I've been thinking about. I think, and you've talked about this a few little points during the interview, but I think it's interesting enough. I want to keep digging on it. Historically, one of the issues that people have with fuzzers is just setting them up and getting them going, right? I mean, it's usually not a fun process unless it's something, it's a pretty heavy context switch for either a security person or a developer, because you're coming at both. And it sounds like you've got some tools in place there to really make that easier, right? I mean, you're using the JSON example, so I'll stick with that. Can you talk a little more about how, if I put my developer hat on and I come in and I've got like some application which is taking, say it's got an API, it's an API server. What does that process actually look like, sort of, the 15-second version of it?
Sure. So that's actually something we've spent a really long time on, is how can we make that process simpler, right? And so right now we've got Go and Rust, where, so for Go and Rust, we've got this working. We want to expand it to other languages. We're pretty confident we can get it on C and C++ this year. And the idea there is you actually don't have to write any code to start fuzzing. So with Go and Rust right now, you would just log in, you'd connect your GitHub account, we'd pull in, you'd see all your code, you'd click on the repo that you want to fuzz, and then what we do is we do a quick analysis on it, where we scan it for kind of all the functions that you've got, the different kind of trying to understand a little bit how your application works. And then we'll list all of those functions to you. And, these are functions that you're familiar with, some of, ideally the ones that you've already written. And you just have to click on them. And then you just click fuzz. And then behind the scenes, what we're doing is doing all the heavy lifting, right? On the instrumentation side, on the fuzz harness side, right? Like actually generating that fuzz test for you. And that's it, right? You click fuzz, and then we'll pull your code, we'll build it on our servers, and then we'll immediately start fuzzing it. And this is a really good way to just kind of do the 0 to 1 process, right? Like you have no idea what fuzzing is. You've never fuzzed before. You don't want to spend a lot of time on it, but you're kind of intrigued, right? You just have to click through some quick setup flow. Doesn't take more than 5 minutes. Honestly, the largest factor is just how long it takes to build your code. So if your code builds, in like 30 seconds, then it won't take you longer than, 3 minutes to go from 0 to actually fuzzing something. And you won't have to write any code. You don't have to think about what it's doing under, how it's like instrumented or how all this stuff is happening. You just click through it. And we found a lot of bugs just doing that. So honestly, like we've the way we tested ourselves is we'll just go in and pull a bunch of GitHub open source GitHub projects, and we'll just click on all the functions that we want to fuzz, and then we'll just fuzz them. And that already in and of itself finds a lot of bugs. If you're not fuzzing your code, bugs tend to pour out the first time just because there are a lot of things that your developers aren't testing for. Once that process is done, then we have these tools that kind of allow you to help you write these fuzz tests. So you can think of like a library that you would pull into your code base and just kind of say, it's just a way to communicate with the fuzzer in a nicer way instead of just working on bytes and, telling it, chop these 15 bytes up and like put them into a string and, cut these up and put them into a struct or whatever. And so on the API side, what I would say is, you probably don't want to fuzz the transport layer, right? Like HTTP, JSON, these are well fuzzed protocols. It's not really interesting to fuzz that stuff. What you want to fuzz is the logic of your API. And so you would want to skip past the transport part and just fuzz directly into the handler, right? And so you can have the fuzzer basically hook into that directly and just provide the data without the JSON part, right? So usually you're working with an object or a struct, and the data would just come structured in that format, and then you just get it fuzzed into that handler. And the idea there is it goes much faster. It's a lot easier for developers to work with. They don't have to deal with looking at weird JSON payloads. These are actual objects that they're familiar with, and you just that's it. It's pretty straightforward.
Cool.
Can you do that for Python so I can get Paul to use it? Oh.
So Python is next on our list. We've got it's fairly straightforward to do. From my understanding, is just because we're an early stage startup, we're focusing more on kind of what our customers are asking for. So if Paul's willing to pay, then maybe.
Good answer. So I've got one more, if I can squeeze one more in here. And this comes back to, you touched upon it a little bit there, but let's see, how do I phrase this? So thinking about that selection of languages you're supporting, and sort of, you've been in this fuzzing space for a while, you know it pretty well. We've talked over the last year or so about the type safe languages we have out there now, or memory safe languages. Like I'll stick, for example, say Go and Rust and maybe TypeScript. I think you do JavaScript, not TypeScript. I'm curious, from what you've seen in your testing and your customers' use, are you seeing the fuzzer finding less issues in these newer languages, or is it just as much of a crapshoot?
It certainly depends on
high level.
Yeah, sure, of course. It certainly depends on the application. Obviously, less or none, memory bugs. But crashes, hangs, timeouts, right? These are very severe. This is where we start to get, once you get into the memory safe territory, that's when you start to get into, how do we tell the fuzzer what kind of define some invariants to the fuzzer, some properties that should never be true. That should always be true. And so that's where it gets really interesting, right? If you've got some, if you take like a very simple like JSON library that just marshals JSON, marshals data into a JSON object and then just unmarshals it, right? If you fuzz just the marshaller, you're only going to look for crashes, for timeouts. If you're just fuzzing the unmarshaller, same idea. But if you're fuzzing you send some data in, you marshal it, and then you unmarshal it, and then you check that the value that came out of the unmarshal is the same as the value that went into the marshaller, right? That produces a lot more interesting types of bugs. And again, sometimes these can be security vulnerabilities. I want to be careful and say, not all of these are security vulnerabilities, but a lot of the times they significantly improve code quality because you don't want these types of kind of bugs lingering in your code. And so going back to the marshaller and unmarshaller case, right? If you've got kind of this inconsistency between the way it's marshaled and then unmarshaled, that's not good. And so these types of bugs and vulns are the types of things we encourage our users to look for when they're actually fuzzing these more memory safe languages.
There's one aspect too I want to talk about, because you mentioned pulling in a bunch of open source projects, fuzzing them. I know Google has done this, but Google also has just about an unbounded budget to run compute resources for this types of fuzzing. Speaking of the compute resources needed to do the fuzzing and the time it may take, how do you handle that and manage that for end users?
Yeah, so I guess one thing I want to be clear about is we were fuzzing open source kind of just on our own, just for us to test our code, right? Like, we are in no way at Google scale when it comes to their resources and their fuzzing efforts for the open source community. Fuzzing, Google's been huge. Like, they've found, I think, like 11,000 bugs. Don't quote me on that. It is public though.
It's something that bugs, large, yeah.
In the open source community, on very large projects, SQLite and like MySQL, all that. So when it comes to, resources, and I think that's kind of a large point for fuzzing is, fuzzing is really resource intensive. Google, I think last I heard, they're fuzzing on like, 20,000 VMs, right? Like 24/7, like, that's not something that most companies can afford. And so what we do is we try to, balance how much fuzzing is done at what stage. So what we do is we try to use fuzzing as a way to generate a corpus or a set of test cases that basically should always be true. If the fuzzer sends in some input, triggers some coverage, but it doesn't necessarily trigger a bug, that could trigger a bug later on in the future when a developer makes a change. So we actually store all of these inputs that don't necessarily trigger bugs now, but could in the future. And so what we do is when you make a pull request or merge request or whatever, depending on your platform, we'll actually run through those previous test cases on that pull request the first thing. And so it's kind of like running regression tests, really. The benefit here is you're using previous fuzz runs to test for bugs again without having to actually run an entire fuzz test job. When it comes to running on master or on main, we want to fuzz as much as we can continuously. And so a large part of this just comes down to how much the customer wants to spend on compute. So if the customer has 10 VMs that they want to fuzz on, but they have 20 fuzz targets, you can imagine it gets really slow if you're fuzzing 20 targets on 10 VMs. And so what we do is we use some proprietary algorithms that basically detect how far along the fuzz tests are statistically, and then kind of deallocate resources to those and reallocate resources to things that are kind of less further along. And the goal is to try and get kind of equal coverage, equal kind of testing across all of the fuzz targets. That's a work in progress, but I think that we've seen a lot of people get really excited about that because it means you don't have to fuzz continuously forever. And if you've been fuzzing for a couple of months, right, like chances are after that point, like you're less likely to find things. We've still found things, but we're just kind of optimizing here for cost more than anything because we're not Google.
Oh. No, but and you're kind of talking about that's what you're working on over the upcoming months. I'm just curious, what do the next few months look like for you? What does 2021 look like for you and for fuzzing?
Sure. For us, we're constantly just trying to improve the developer experience with fuzzing. So, making it easier. Like I said, we've got it working for Go and Rust, kind of just click through fuzzing. Python is next. Click through fuzzing for Python might be a little bit trickier just because there's no types. So we'll have to kind of do like some work around there. So definitely on the easy side, definitely increasing the class of bugs that we find. So one thing that we started testing with and we've seen it work really successfully, and we want to kind of extend this, is floating point, like fuzzing against floating point math, and kind of anywhere you're using floating points, checking that things are kind of the math checks out, right? That's fairly interesting and can lead to vulnerabilities, but certainly lead to just kind of bugs that you don't want in your code. So that's kind of one thing that we're doing is I'd like to call them maybe sanitizers. And so just building more of these sanitizers out that we can use to find more interesting bugs with less effort from the developer, right? That's something that we're focusing on this year. And then, in the fuzzing community, I think they're starting to catch up on like making tools easier to use. I think there's still a very large focus on making them more effective. I think, more effective fuzzers is really useful, but if no one's running them, then they're actually not more effective at all. So our goal from FuzzBuzz is, right, let's get people using them, and then let's make them more effective. And we're constantly looking at the research that's coming out, around making it, squeezing out just a little bit more speed, or adding some algorithm that goes a little bit, a little deeper into your code base or something. We've also seen an interesting rise in grammar fuzzing. So if you can define a grammar for it, you can try and fuzz within that grammar. That, again, gets a lot of interesting results if you've got these weird, obscure protocols or definitions of kind of specs that you need to use. So I think that's probably where we're headed in 2021. But we'll see. Cool. It's kind of early.
We'll see. Yeah, well, I think we're also going to have to demonstrate the halting problem right now and bring this segment to an end. So, right. Andrei, I do want to thank you for joining us. This was a great talk about fuzzing.
Yeah, it was great being here. Great to talk about it, and I hope more fuzzing in the future.
Hope so. You also dropped the phrase fuzz run, so I'm trying to think through what type of synthwave subgenre fuzz run is going to be. So thank you for that as well. Also want to thank Matt and John for joining me, and thank all of you for listening. We're going to take a quick break and return with the news of the week.